let's stay with waves and continue with Paul Stocker. Paul Stocker is really a connection between different NGSolve places. So he's done his PhD in Vienna with Ilaria Perugia. This he moved to Göttingen to work with Christoph Leonfeld. Spent a while also in Pavia, selling NGSolve in Pavia. And
yeah. Cool. Okay, thanks Joachim. Thank you for the introduction. Yes, so yeah, I'm going to present NGSTrefftz, the add-on for Trefftz methods in NGSolve. Yeah, I've been developing this package starting with my PhD in 2018. Since then, it has been in continuous development. So as Joachim said, during my PhD with Christoph in Göttingen, and yeah, several collaborators have already contributed to the package. You can try out the package easily. There's a pip install. NGSTrefftz, so and several notebooks are available. There's the source code available, and several notebooks to try out. I'm going with the old school version of slides to just show, yeah, explain a bit more about the methods themselves. But there are a lot of notebooks you can try if you want to. Okay, so the overview of my talk. First, I want to explain to you what are the Trefftz discontinuous Galerkin methods we're interested in. Show how Trefftz spaces work in NGSolve. Then we have a few extensions, two extensions that I want to discuss, quasi-Trefftz methods and embedded Trefftz methods. And then also the Trefftz package has some nice interfaces with other packages of add-ons to NGSolve, namely NGSTrefftz, which Jay will present directly after me, and NGSXFEM, so the XFEM methods from Christoph that he will present tomorrow. Yeah. Okay, so the first question, what are Trefftz methods, TrefftZG methods? So what we are thinking of when we talk about these TrefftZG methods is, as a starting point, we have our standard PDE, linear operator, and DG discretization. And DG, of course, so you've seen a lot of DG already yesterday and today, meaning we have element-wise basis functions that are only coupled through jumps and averages over the boundaries of our elements. And the Trefftz part comes from the idea of replacing these standard polynomial functions inside each element with a Trefftz space. The Trefftz space should be a subspace of the kernel of your operator. This will guarantee that you have optimal approximation properties, usually, and a good reduction of degrees of freedom compared to the full polynomial space. So usually, so in general, one can say that in most cases we get a reduction of p to the power of n minus 1 compared to p to the power of n from the full polynomials. And we keep the approximation properties, so the same convergence rates that we see for the full polynomial space. Okay, so a quick example for this. Let's say we are just looking at the Laplace operator and our standard symmetric interior penalty formulation that everyone knows. Then, as a Trefftz space, instead of the full polynomials, we could choose the harmonic polynomials. So simply 1 xy, xy, and then these are the harmonic guys. So x squared minus y squared would be harmonic, and then we have the third order guys. Yeah. So this means we have to implement these harmonic functions into NGSolve, and then we can use them with our DG formulations that we already have in NGSolve. So what are then these other Trefftz methods I've already been mentioning at the beginning of my talk? So the Trefftz methods, as I was saying, they lie in the kernel of the operator, but they have some glaring weaknesses that we are trying to overcome with these other methods. So first of all, if you have varying coefficients in your PDE, you will run into troubles when you try to find suitable discrete basis functions so they will not be polynomial anymore. And constructing them will be very difficult, so usually we cannot treat varying coefficients. Of course, we are looking at functions that are in the kernel of our operator, so they will not approximate well once we have a right-hand side involved. Yeah, so, and the benefits of TrefftZG, of course, so we have explicit basis functions usually if we have constant coefficients and no right-hand sides that approximate well. Now compare this to the other two methods that I want to go into detail in my talk with. So we have a quasi-Trefftz and embedded Trefftz, and both solve some problems that we have with the standard TrefftZG methods. So instead of being exactly inside the kernel of the operator, we will have to relax this condition for us to allow for varying coefficients, also treat the right-hand side. And then the difference between these two methods is that we still have an explicit basis for the quasi-Trefftz, which I marked in yellow, since this, of course, means that we have to implement these guys. And, of course, we usually don't find a well-conditioned basis, so this can be troublesome. Whereas for the embedded Trefftz method, while there is an X, I still put it in green, since there we will not have to construct explicitly these basis functions, but circumvent this by doing SVD. So the additional cost for these two methods is element-wise, we need either a Taylor expansion of our coefficients, or we need to do an element-wise SVD, which you will see later on. Okay, so this is the overview. I will start with the Trefftz spaces, so standard Trefftz spaces, and how to implement them in NGSolve, and then we will look into these other two methods. Okay, so in Python, we can simply run, once you have run pip install NGSTrefftz, from NGSTrefftz import star, and then we have available these Trefftz finite element spaces. They behave like the L2 spaces that you already know, so meaning they are DG spaces. We will give them the flag DG jumps true, and then we can use them in our bilinear forms as we are used to. The additional flag that you have to tell them is which equation, or with respect to which equation they are supposed to be Trefftz for. And we have several implemented. So you have harmonic polynomials for the Laplace, but you also have, for Helmholtz, we have plane waves, so non-polynomial functions. We have wave polynomials for the wave equation. We also have heat equation implemented. So there are several to choose from to use with your DG formulation. For any order. Okay, so this goes into your standard bilinear form, and you can use them as usual. What happens under the hood? So just to give you a hint on the C++ side, of course, what we don't want to do with these element-wise spaces is transform them back to a reference element, since this would we would lose our Trefftz properties, so we would not be in the kernel anymore if we transform under the operator. So on the C++ side, we have a scalar mapped element that behaves like the scalar element from NGSolve, but is evaluated directly on the physical element instead of using a reference element. Okay, and on this, we then construct our Trefftz basis functions. Okay, so let's have a look at the first extension of the method, the quasi-Trefftz functions. So as I've been saying, if we have varying coefficients, we would run into trouble with this first approach. So what we want to do instead is look at polynomial basis functions that have a relaxed condition. So instead of satisfying the operator equal to a right-hand side 0 or f explicitly or exactly, we want to relax this condition by taking here the derivatives and then evaluating in the center of the element, meaning that the Taylor expansion of the operator applied to our function vanishes up to a certain degree. This condition actually allows us to find a recursive formula for the coefficient, so we can actually construct these basis functions, these polynomials that satisfy these equations, this set of equations, and this gives us a quasi-Trefftz basis. This will work for varying coefficients, and by constructing a particular solution with respect to this right-hand side, we can also construct this affine space with an f, allowing us to solve an equation with the right-hand side. Okay? So the test functions would still be in a 0 right-hand side, and then we would have one affine solution that lives in this space to approximate the right-hand side. This is how we use the quasi-Trefftz space. So here are just some nice pictures on how we're going to use it. Same command, Trefftz FA space, but instead of asking for the equation for the wave equation, we are now just putting the quasi-Trefftz inside here. This will give us the quasi-Trefftz spaces functions. We then pass a varying coefficient, say y plus 1. And now we're solving the wave equation here with a changing wave speed, so with increasing wave speed in y direction. So you can see that this wave that usually would propagate, looking like this, we have that the speed is, so it's propagating fast on top than on the bottom, so you get this slanted wave. So we have the Trefftz polynomials approximate this wave optimally, compared to using a linear, a constant approximation of this coefficient with the normal wave polynomials. Okay, yes, and we have this implemented for the wave equation, and so it's a spacetime method. And for the elliptic, for any elliptic equation, we also have this recursion formula implemented. Okay, so yes, with the Trefftz and quasi-Trefftz stuff out of the way, now I want to talk about the embedded Trefftz method. So as I was saying in the beginning, the idea here is to completely circumvent the explicit construction of these Trefftz basis functions, right? So what do we want to do instead? Our goal is to represent the Trefftz basis functions inside our standard DG basis. So we want to construct an embedding. So this is why we call it the embedded Trefftz DG method. An embedding that maps our standard DG basis in blue onto our Trefftz basis functions in green. All right? This embedding should be an element-wise operator. Then, instead of solving our standard DG system, so here written in a linear system form, we then project the system down onto a Trefftz space by multiplying, by plugging in from left and right this projection operator, this embedding. And then we only solve on the much smaller system, which is TAT, so on the Trefftz space. Again, the dimension of the Trefftz space is much smaller than the dimension of the full polynomial space, right? Now, how can we construct this embedding? This is the main question. The recipe for this will be, so of course we want that the operator L applied to our U is equal to 0, which is of course equivalent in testing with any V. So L of U and L of V has to be 0, and this we can put into our bilinear form. So this element-wise bilinear form, we then need to find the kernel of. And finding the kernel of this guy we can do, as I mentioned, with a singular value decomposition and looking at the 0 singular values. So again, this is only element-wise. These matrices are small. We are doing this on an element-wise level. We're looking at the 0 block down there. So these are the 0 singular values. And then the embedding will be given by this lower block down here. And we can assemble the full projection by taking these blocks. So it will be a block diagonal matrix that will give us the embedding. Another thing to notice already is that these basis vectors will be orthogonal. So we indeed keep the conditioning of the system from the polynomials, so that we start from. Meaning compared to the standard Trefftz space where we construct these functions by hand and usually mess up the conditioning a little by doing so. Here we can conserve or even only improve upon the conditioning of the full polynomials. Okay, so I've been also telling you that we can use this even in the case for right-hand side or non-constant coefficient. So let's have a look what we can do with this idea once we have a right-hand side involved in our PDE. If we have a right-hand side, we can still use our SVD that we already constructed, but now we're looking at the upper block to construct the pseudo-inverse. So we can construct element-wise a particular solution simply by taking the pseudo-inverse from the already computed SVD. With this particular solution, which is again an element-wise guy, we can homogenize the system, so simply subtracting this from the right-hand side. We can then again solve with the Trefftz space for 0 right-hand side, right? So now what can we do with operators where the Trefftz space is non-polynomial? So change varying coefficients, or also the Helmholtz equation where the Trefftz space typically cannot be polynomial. We can still treat this with the embedded Trefftz method by considering by again weakening the condition in the space. So there's a similar ideas for causa Trefftz, but we are weakening in a different way. What we want to do now is project onto a smaller subspace to test with. So instead of testing with the L of V here, we will instead test with a W that is in a smaller space than the VH. Yeah? Of course, let's consider simply the Laplace without a varying coefficient. Then this is equivalent to putting the L here and choosing or choosing the polynomials of p minus 2, since the Laplace maps from polynomials of p to polynomials of order p minus 2. So this would be completely equivalent in the case of constant coefficients. If you have a varying coefficient, then only this is a sensible way that will give us a complete basis that gives optimal approximation properties. Okay, so this replacing our previous matrix W that we look for the kernel by this one, we now can construct an embedding for this weak Trefftz space. So the Trefftz space with this projection inside. And this gives us the option to treat also Helmholtz equation and varying coefficients. So let's have a look at the examples here. This is the example for Helmholtz equation. We are comparing to the full polynomials the plane waves and the weak Trefftz space that I've just showed you. So the plane waves, to remind you, are these exponential functions. These solve the Helmholtz equation exactly. Then we have the weak Trefftz space, which is simply the projection of a p minus 2 L2 projection of the operator to a function b. This is what the embedded Trefftz method gives us. And then in violet, we have the full polynomial space. Yeah. First of all, looking on the left-hand side, we see optimal convergence rates for all of the spaces. However, there's already some curiosity that we can observe. So looking at the dashed line, which is order 4, we see that the full polynomials have a larger error by a constant than the embedded Trefftz space. So even though the embedded Trefftz functions, a polynomial space that is a subspace of the polynomials, seems to gain some stability akin to the plane waves, which they share the error with, right? They deliver the same error as the plane waves, even though they're only a subspace of the polynomials here. Now, looking at the right-hand side, we're looking at the convergence in P, polynomial degree or number of plane waves. You can see that the plane waves, at some point, they will be ill-conditioned. So you can see here in turquoise for order 5 of the plane waves, we see that, so I didn't do any fancy tricks, I didn't do any preconditioning, but they will, the ill-conditioning shows and the error stops to converge. Whereas I've been telling you earlier that we preserve the conditioning of the polynomial space, so the embedded Trefftz method still shows nice convergence when compared, as the full polynomials, right? Okay. How does the implementation NGSolve look? We actually have 2 different implementations at the moment, but the nicer one to explain is this one. So here is the pseudocode on the left-hand side. Right-hand side is how it looks in NGSolve. The idea was we want to construct an embedding that looks like this, and possibly also a particular solution, and then solve this kind of system, right? For this, we have a function in NGSolve now called Trefftz embedding. You simply pass 2 sums of integral, so the ones that you want to use to construct the embedding. We then get these embedding matrices that we can multiply to our system matrix and then solve exactly the system I've been showing you earlier. Of course, this is not the most optimal way of doing things, since here we are still setting up the full DG system matrix and the multiplying afterwards. We can also construct this matrix already during the assembly, which I've also implemented. Is currently only working for scalar spaces, so not vectorial, and you can find it in the notebooks. Okay. Yes, one more example, just to show some timings. Again, Laplace equation, optimal convergence rates for embedded Trefftz, polynomials, and Trefftz space. And here I'm just comparing a timing of the time we take to solve the full linear system, the assembly time, and then, of course, the main question would be how much time am I spending on doing this element-wise SVD. Here I'm using, I think, 8 cores in parallel, threads in parallel. And you can see this orange line here, possibly you can see it, is the SVD, which pales in comparison to the time that we need to solve the full system. Okay, so yes, to finish, I just want to show 2 more applications where we combine these Trefftz functions with NGSTrefftz and XFEM. So tent pitching, which Jay will explain in a moment, so I will not go into detail, is a space-time meshing strategy that constructs these tents in space and time. So we have time going upwards, is for hyperbolic equations, and gives optimal time step sizes for each mesh element. We can construct these using NGSTrefftz. So this is what Jay will explain in a second. We can construct these tent slabs that we then want to solve on with the Trefftz method. And this is exactly what we've done. So you can use this tent slab with a function called Trefftz wave, just passing this tent slab, the order you want to solve with, and the coefficient function, which is the wave speed of your wave, will then allow you to propagate on these tents using Trefftz basis functions to solve on each element, so this is one of those tents, to solve on each element using Trefftz basis functions instead of full polynomials. Okay. Second application, or second combination, I should say, with NGSXFEM. So one nice thing of using Trefftz as a reduction technique for DG is that it keeps all your degrees of freedom still as volume degrees of freedom. So it doesn't care what happens on the edges per se. So it easily combines with unfitted techniques. So the package, yes, NGSXfirm, that Christoph will present tomorrow, allows us to construct unfitted geometries. So like this, let's say our geometry is this circle, which is as an unfitted geometry inside of this mesh as a level set function. Then we can represent it using NGSXfirm like so. And we can still solve on this set also with the Trefftz finite element spaces. And so, yeah, do the standard techniques that Christoph will explain tomorrow to condense also this space only onto functions on this circle and so on. It easily combines with the stabilization techniques that you use. So if you have a small cuts on the elements, you would need to do either of two things. So the most popular stabilization techniques are element aggregation or ghost penalty. Both work fine with the Trefftz spaces. So element aggregation simply means you combine the small cut element with the neighboring element by gluing them together. Ghost penalty means you introduce another term into your bilinear form, this ghost penalty term. There are several choices that you can take, but all of them easily combine using the Trefftz space instead of the L2 space. Okay, with this, I want to conclude. So you can find all the notebooks and the full documentation on the website. You can try all the notebooks yourself. As I was saying, you can use pip install. We have used these and presented these methods in several papers, specifically the embedded Trefftz paper for the embedded Trefftz method I've been showing you, and 10 pitching here. And then recently we did, we applied it to Stokes, and also we did a nice comparison of the sparsity pattern of these like polytopic finite element methods like TrefftZ and so on in this work. Okay, yeah, thank you so much.
Thank you very much. Questions?
So architecture. You showed us the timing on a certain architecture. I guess it was CPU.
Yes.
Do you expect your method to improve with GPU due to the fact that it seems extremely, or on modern architecture, right?
Yes.
It seems extremely fitting with the way modern architecture are developed.
Yes, for sure. So with the SVD that is only element-wise, it parallelizes extremely well. So I would expect that it works nicely with any way that you want to choose to parallelize your stuff. Yeah.
Another method was a common case to move to GPU.
Please. Yes. Yes. Yeah. Now I have to make an appointment.
The examples from the online material is more or less what you presented in the talk.
Yes, and much more. So we applied it to a bunch of equations.
You can
yes, you can rerun everything. Yeah. Yes.
Okay. Then and you will present a tutorial to people who are interested on Wednesday also, and you ready to try this methods out on. Particularly on Wednesday.
Yeah. Great. Okay.
Okay. Then thank you, Paul. And
thanks.
Thank you.